Hello and welcome to IST Decrypt's Intro to Deep Learning. Our topic for today is logistic regression. So let's get started. Logistic regression is most commonly used to classify data with a binary output, which means we have two class labels, 0 or 1. For example, a computer program that acts as a cat versus dog image classifier. The input image is a picture and it either identifies a cat or a dog, no other option. It has a binary output. This is different from linear regression where the prediction value is continuous. In logistic regression, we look to fit a curve to the data and try to achieve the best possible fit. This curve is called a sigmoid function, as given here. S of x is equal to 1 by 1 plus e to the negative x. Now, the special property of this function is that for x ranging from minus infinity to infinity, this function is bounded between 0 and 1. And we can clearly see that because here if x tends to positive infinity, then this e to the negative x term vanishes to 0, and we have the function value approaching 1. And if x tends to negative infinity, we have e to the negative x approaching positive infinity, or the whole function approaching 0. So using this sigmoid function, we can use it to fit a particular curve for our data set. Over here, we have a very simple example of logistic regression. Given an age, we have to calculate whether that particular individual has health insurance. So these green points are the points in our data set. Let's say that this age is 19, this age is 17, this age is 15, and so on. This is 51, this is 52, this is 53, and so on. We want to find a curve that fits this data for new data points in our data set. Here clearly we can see that for the age of 19, the probability of having health insurance is very close to 0, or basically 0. And for an age of here 51, it is equal to 1. Now, if we have a new value, say the age is about 23, our sigmoid function should give us a predicted probability of them having insurance. If this predicted value is greater than our threshold value, in this example it's 0.5, it will be given a positive label of 1, and if it's not, it will be given 0. So here 0.3 will be classified as not having health insurance because it's below the threshold value. Similarly, an age which produces a y value of 0.8 will have a label of having health insurance as true or 1. Now, this is a very simple example of logistic regression because we only have one input parameter called the age. Generally, in machine learning problems, we'll have several input parameters. It could be ranging from a few thousand to a million. But when we have more than one input parameter, we can no longer draw a 2D graph. If we have two input parameters and we want to show the output, we'll have to draw a 3D surface. And if we have more than two input parameters, we can no longer visualize it easily. But still, mathematically, we can predict the output value. And that's what majority of our logistic regression problems that we'll see, that's the kind of data we'll be working with. So now, just to drive the point home further, of why we use a sigmoid function and not a linear line for this classification example is, as you can see here, the line does not really do a good job of covering our points in our data set as compared to our sigmoid function. Here, a simple y equal to mx plus b curve is given. And you can see that the straight line does not give a good approximation of this function. But when we feed this straight line into our sigmoid function, 1 by 1 plus e to the negative, instead of x, we have y here, which is mx plus b. We get our sigmoid function. And you can see that this does a pretty good job of fitting our curve. Now, for a more real example, instead of our previous example with only one input parameter, let's say our input is a vector or a matrix, basically a group of input values, not a single one. Say, for example, the pixel values of an image. W of t is the array of weights, and b is the constant that is added, very similar to the linear regression equation, y equal to w of t x plus b. So what w of t into x should give us is w1 into x1 plus w2 into x2 plus w3 into x3, and so on. And we add our bias term at the end, b. Here we feed into the sigmoid function. And our logistic regression model should give us the probability of us having y equal to 1 given our input vector x, which is equal to 1 by 1 plus e to the negative w transpose x plus b. Now, to find out what we want as our weights and our bias, we need to have something known as a loss function. And what our loss function gives us is the error between a predicted output y and the actual output. No, the predicted output y dash and the actual output y. Based on this, we can get a sense of how good our model is of fitting our data. And the lower the loss function, the better the model is. So we need to try to make our loss function as low as possible. Our loss function is basically an error function, which gives us the difference between our real value of y and our predicted value of y dash. So loss function of y dash comma y is equal to minus log y dash plus 1 minus y log 1 minus y dash. This might look like a big equation, but it's actually pretty simple. It's just two very similar terms that are added to each other. Y log y dash plus 1 minus y log 1 minus y dash. And to get a sense of why this is true, as I previously just told, we want the loss function to be as low as possible, especially when our inputs are correct for our graph. So when y equal to 1, that is, say we have a label that we want to be classified as true, the loss function equates to L y dash comma y equal to minus log y dash. And here we want minus log y dash to be as small as possible when y dash is actually correct, or y dash is approaching 1. And we know that for larger y dash, negative log y dash will decrease. So this is a good equation. Similarly, when y equal to 0, we want, when our y dash is closer to 0 or an accurate prediction is going to be made, we want this full equation to have a smaller value, which is true when y dash is smaller. So the main takeaway is that we need a loss function for our logistic regression model, and this loss function is given as this equation. The most important point here to remember is that the loss function is a measure of the difference between the predicted output value and the actual output value. And we want to reduce this value to make our model better. Basically, a model that produces less error. Okay, so if we understood the loss function, then the cost function is very similar. The loss function is used for each and every input training example during the training process, whereas the cost function is used for the whole training dataset in one iteration. Here we sum up m training examples, j of w comma b. So given like our weights and our bias, we want to find the loss. That's equal to L of y dash of I comma y of I, and we take the sum from I equal to 1 to m. Basically, for all our training examples, we want to find the loss. So we take the sum. The objective of the training network, this is a very key point, is to find the weight matrix W and bias B such that the value of the cost function J is minimized. We want to reduce the cost or the error that the model is producing, and we need to find a way to make those weights and the bias correct for that particular use. Yes, so the way that we do this, the way that we obtain the minimum or the optimal weights and bias starting from a random weight matrix is done using gradient descent. So the process of gradient descent is as follows. We first initialize our weight matrix randomly, then we use gradient descent to find weights W and B that minimizes the cost function. And gradient descent is just based on calculus. We have our slope here. This curve is actually the plot between the cost function and W, and we want to find the minimum value of the cost function. And as you can see, there will be a particular set of weights and bias at which this happens. Our gradient descent algorithm, wherever we start, will give us the slope or the tangent at every point using calculus to take small steps and slowly arrive at the optimum set of weights or the lowest point. And for that, we use this procedure. W is equal to W minus the derivative of J with respect to W. It's actually the partial derivative because W is not the only parameter it depends on. But the main takeaway is that we are finding the change in W that changes W, the cost function the most. And the same for B. B is equal to B minus partial derivative of B with respect to B. So how do we change B such that there's maximum change to the cost function? How do we change W such that there's maximum change to the cost function? And you must have noticed that we multiply this with alpha. What alpha does is it allows us to control the step. If we want to decrease the derivative by a very small amount, we use a small alpha. And if we use a large alpha, we descend down our slope very quickly. For example, in this diagram, if alpha is large, we will be taking large steps to reach the bottom, but we might never reach the bottom perfectly. And if alpha is small, we ensure that we reach the optimal value of the weights, but it might take more time with a very, very small alpha. We'll have to run more iterations. And yeah, this is how the loss function looks. And also, the reason why we chose that particular loss function, even if it looks a little bit random, is that this particular loss function gives us this particular plot. When we plot W with the cost function, so it allows us to have one single local minimum and not several single minimas. Okay, so if you understood till here, the majority part is done. And if you have any doubts in the basic understanding of the loss function or gradient descent, just pause and rewind the video and watch it again, because the major concept part is over. Now we'll just be looking at how the gradient descent algorithm works and the mathematics behind it. But already all the intuition has been built up. So let us summarize all the equations that we know so far. Z is equal to W transpose X plus B. Y dash is equal to A is equal to sigma of Z, or the sigmoid function of Z, and our loss function that we saw previously. The first equation denotes the products of an input vector X with a matrix W and a bias B. Pretty simple. Second equation is a sigmoid activation function, which we saw before, 1 by 1 plus e to the negative x, which introduces non-linearity, which is very important. The third equation is the loss function, which calculates a loss between a given y and a predicted y dash. Right? That is the key takeaway of the loss function. It gives us the loss between a given y and the predicted y, and we want that to be minimum. Now, these equations can be modeled using a graph. I'm sure you've seen something like this in the earlier videos of this series. Not the computation graph, but just how these neurons attach and how they propagate. We can model these equations using a computation graph. For simplicity, let us consider that there are two features, x1 and x2. given an input matrix X. Accordingly, there will be two weights, W1 and W2, in the weight matrix W. So for now, ignore all the red lines and only look at the black lines. What we have is we feed in these values of X and W, and we get our value of Z. Then from Z, we compute A by taking a sigmoid of the function, and then we find the cost of A comma Y. Now, what we want is to reduce our cost function, right? Because initially we start with a random weight matrix, and we want to find the optimal value of the weights. And the way we do that is using gradient descent. And this is the simple backtracking procedure. So first we want to find out what change in A we need to make to reduce the loss function. Since A depends on Z, we need to find out what change in Z we have to make to change A, which in turn changes the cost function. And for that, we need to find out what change in each of the weights and the bias we have to make to change the input Z, to change the input A, which in turn changes the cost function. And that is what the gradient descent algorithm does. As you can see right up top, we have the loss function given here, so it will just make this process easier. We know that the loss L depends on A. First, we can calculate the derivative A, which represents the derivative of L with respect to A, using equation 3 as follows. So we have dA, like we want to find dA, like the change in A we need to make to produce a change in loss function, is equal to partial derivative of L with respect to A. And now this is equal to, let us look at our loss function. If we want to take the partial derivative with respect to A, we have y as a constant. So looking at only the inside term, we have 1 by A into y plus 1 minus y is a constant here into 1 minus 1 divided by 1 minus A into the derivative of the inside term, which is minus 1, using the product rule and the property that derivative of log x is 1 by x with respect to x. So I encourage you to work this out yourself and take the partial derivative of the cost function with respect to A, and you will notice that this is the exact value you get, dA. Similarly, for dz, we have the formula, and what we can do to find dz is that we can write it as derivative of L with respect to A into partial derivative of A with respect to Z, because these two terms cancel out. This is the chain rule in calculus, is equal to A minus Y. And you can see the explanation in the next slide. What A is actually equal to is sigmoid of Z, which is 1 by 1 plus e to the negative Z. And if we take the derivative of 1 by 1 plus e to the negative Z with respect to Z, we get this term. You can try it out yourself if you know how to solve basic calculus problems. It shouldn't be much of a problem. First, we assume that the bottom is just x. So we have the derivative of 1 by x is minus 1 by x squared. And then we find the derivative of the inside part and multiply it. So we get minus 1 divided by 1 plus e to the negative z whole squared into e to the negative z into minus 1, which will give you this. Rewriting this as a into 1 minus a, because a is equal to 1 by 1 plus e to the negative z. You can try it out for yourself, or you can just take my word for it. This is the correct answer. Now d of z again is this. A into is equal to a minus y, because dA by dz is a into 1 minus y, and we have dA equal to this term. And if you do the simplification, you will notice that dz is equal to a minus y. Now the maths continues. We are almost done, but the only thing left to do now is to find, as you remember, we found dA, dz, but now we want to find the changes that we have to make, the initial weights and the bias. That's the last step. How do we change the weights and the bias to produce a change in the loss function. And again, calculus and more of the chain rule. Remember, z is equal to w1x1 summation plus b. dw1 is given as derivative of the loss function with respect to w1 is equal to the derivative of the loss function with respect to dz into dz by del w1. This is the chain rule, and we already calculated most of this. We know that derivative of L with respect to z is equal to a minus y, and it's very easy to see that derivative of z with respect to w1 is just x1 because all other terms are constant, and w1 x1 is the coefficient of w1. Hence we get this formula x1 into dz because a minus y is dz. And we go on for all the weights. In our case, only 2 weights, but this generalizes to m weights, or how many ever weights we have. And very similarly, we calculate db as the derivative of L with respect to b is equal to the derivative of L with respect to z into the derivative of z with respect to b is equal to a minus y, as there's no coefficient for b, so we won't get an x term in front, is equal to dz. And we are almost done now. Now that we have found all the derivatives, we need to update the weights and bias with the help of gradient descent as follows. W1 is equal to W1 minus alpha into dW1. W2 is equal to W2 minus alpha into dW2, and B is equal to B minus alpha dB. So this is the gradient descent algorithm into work. We find the derivative. We find how to optimally change, like the intuition, to repeat once again, is we find how to optimally change the weights using the slope to find the optimal movement from the position. I'll just keep the graph in picture. Yeah. So for each particular weight, we want to know which step to take to reduce the weight and slowly bring it to the optimal value of the weight to reduce the cost function overall. And we apply that to all the weights and the bias to get the lowest possible value of the cost function. That is how the gradient descent algorithm works. And we are basically done, except note that we were talking about the loss function, and instead we need to know the formula for the cost function, which is for all the training examples together, which is simply the sum of all the training examples. And so we are basically done. Don't get scared by these big formulas. It's already done. We already know these answers. During the training process, we need to minimize the cost j, and this can be done by minimizing the loss L for each training example I over all the m training examples. As the loss function L itself depends on the weights W1, W2, and B, we have to minimize j with respect to the weights W1 and W2 and the bias B as follows. So j is our cost function, right? Given W and B, we want to know how to minimize that with respect to W1. And the formulas for that is given here. And with this, we have ended our discussion on logistic regression. And this is just a simple pseudocode to sum up everything that we do. We first initialize a cost to 0, all our changes in weights to 0, and we run our algorithm. And finally, we have our output of the model as our weights and bias, W1, W2, and B. We've discussed the proof of all these formula, and we can easily implement this in Python, or we can use a pre-trained model again in Python using something called scikit-learn. But just remember, when you're coding, it's much easier if you know the concepts. Then the coding will feel a lot more intuitive, and that's why we had this video. Since there was a lot of maths, it's important to not get lost in all the math and just focus on the core understanding of the material, which is the concept of the loss function and gradient descent, and how what gradient descent is actually doing is just reducing the loss or the error function, which in turn makes our model better. And that's all there is to logistic regression. So that'll be all for today. Thank you.